I changed the title of my talk a little bit. Yeah, I'm going to talk about implementation of non-universal star formation prescription in galaxy formation simulations. I'm doing this work at the University of Chicago with Andrei Kravtsov and Nick Nedin. Yeah, and star formation prescription is as important part of stellar feedback loop as a recipe for feedback itself. And the feedback models are being refined for years. We had a special session on this, and we see that these models become more and more complicated. However, for star formation prescription, we use the same prescription which we used 20 years ago. Basically, we parameterize star formation rate as an efficiency at which a gas is converted into stars at freefall time. And for this parameter, star formation efficiency, we assume that it's universal at level of few %, and we confine by hand star formation only to regions of cold and dense gas. So these temperature and density thresholds are usually set by hand. Sometimes other thresholds applied, like gravitational boundiness or convergence of velocities, but the general picture is usually the same. So we assume constant star formation efficiency. And this is what we have in simulations and what's happening in real life. In real GMCs, we see something like this. So picture is much more complicated. Stars are forming in supersonic turbulence. There's a huge variety of physical processes involved at these scales. So relevant scales are from several parsecs to several hundred parsecs, and these scales are not resolved in modern galaxy formation simulations. And all this complicated physics is absorbed into this simple model of universal star formation efficiency. Whether it's a valid assumption, whether it's fair or not, it's questionable. However, simulations of such objects, of GMCs, can shed some light on this question, and this work is being done. So people basically just simulate supersonic turbulence in periodic boxes with a high resolution. They add magnetic fields, they add self-gravity, and they mimic star formation as a thin particles, and they can just calculate how much mass is formed in these boxes and assign star formation efficiency for different conditions. And these authors, Padon and the collaborators, a few years ago found the general trend that that star formation efficiency exponentially decreases with increasing importance of turbulence in comparison to gravity in such simulations. So they express this importance as the ratio of relevant time scale. So for gravity, it's freefall time. For turbulence, it's turbulent crossing time. And if expressed in terms of this parameter, this dependence of efficiency, it basically is just exponential. Similar simulations done by other authors basically agrees with this general trend. And so this is good. This model tells us that efficiency does vary with varying turbulent properties of GMCs. This model, in principle, can be implemented in galaxy formation simulations if we had some knowledge about turbulence on scales of GMC. So freefall time is easily accessible because it depends only on density. On the other hand, crossing time depends on unresolved turbulent velocities. So as I said, scales of GMCs are not resolved, and therefore the turbulence must be treated by a subgrid model. Such models do exist. They're well known in engineering, in simulations of terrestrial flows. And we implemented one of such models, nicely described by Schmidt and collaborators. Basically, in this model, apart from basic hydrodynamical quantities like density, momentum, and energies, a new field is self-consistently evolved. So this field is associated with the unresolved turbulent energy. And the entire set of equations looks like this. So don't look at the equations. look at the colors. So black colors are basic inviscid hydrodynamics, and all blue terms are those which arises from the subgrid turbulence. So this is just to show that the model is quite complicated. There's quite a bit of machinery behind it. And this model includes, so the turbulence is coupled to resolved motions. It's sourced by turbulent cascade from resolved motions into subgrid scales. It can be sourced also from small scales by supernova. It takes into account turbulent pressure, turbulent diffusion of energy, and also in this model, turbulence decays into heat over a physically motivated time scale. So, as you might guess, I work with ART code, and I implemented this model in ART, and output of this model I used to predict star formation efficiency. I use it to simulate isolated disk galaxy using Agor initial conditions. And this, what I have, this is the gas density and gas temperature. In this particular simulation, I had resolution of 40 parsecs. So this is the scale of the largest GMCs. And the turbulence at these scales is modeled by the subgrid model I just showed you. Basically, what this model does, it takes the disk dynamics and predicts how many unresolved turbulence is there in each cell. So using this information, we can deduce crossing time and use this crossing time as an input into this model for star formation efficiency. And to show the power of this model, let's consider, for example, these two spiral arms, this one and this one. So these two spiral arms have comparable densities and comparable temperature. So if we apply usual star formation prescription based on temperature and density thresholds, we'll get that these two arms form stars equally efficient. However, let's see what this model does. So this is the predicted star formation efficiency, and we can see that one of the arms do form stars, while the other almost doesn't. And the difference is in different properties of turbulence. So model predicts different level of turbulent velocities and these two spiral arms. And now we can compare this distribution of star formation efficiency with what is observed. So I plot the distribution of gas surface density versus the star formation rates at scale of individual cells. So the first noticeable feature is that star formation efficiency varies quite a bit by orders of magnitude. So the diagonal lines are constant efficiencies per free-fall time, and we can see that in my simulation it reaches values as high as 10%, while the most of the star forming gas sitting at level of few percent. And we can also see that the threshold of temperature arises naturally because star formation is possible only in supersonic turbulence and therefore in cold medium. And we can just compare this to what is observed in local GMCs. So local GMCs do fall on the upper envelope. So this we should remember that local GMCs is quite biased sample because it's the largest, it's brightest GMCs, and not surprisingly, they're also the most efficient. More fair sample would be blind searches for GMCs or extragalactic results, and these extragalactic star formation maps do agree with this general distribution. And for field comparison, we can average the star formation rates over larger patches, say kiloparsec size patches, and then compare it to observed Kenny-Kachmit relation. And without any tuning, this model do predict correct normalization and overall trend. So I think this is quite promising. Yeah, and I'll leave you with my summary. So this turbulent model of star formation do predict variation of star formation efficiency. It introduces natural threshold of temperature without any artificial threshold set by hand, and the overall distribution does agree with the observations. Thank you.
Question mark. When you're making your surface density maps, especially with the 40 parsecs, can you clarify a little bit more how you're defining surface density? Are you taking 40 parsec pixels looking down on the galactic disk, or?
I just take the cell. I know the density in the cell, so I multiply it by size, and I assume that it's surface density.
Okay.
So it's local surface density.
Okay, so it's simply the volume density of the cell multiplied by its size.
Yeah.
Okay, so I think the reason that you're probably offset from the local ones is that that's not quite equivalent to the way people are making those local ones. I mean, I wouldn't sort of put an epsilon FF through those local ones analyzed that way because it's not really
Sure. Sure, yeah, it depends on sizes of GMCs.
Those are all much smaller than 40 parsecs.
Yeah, that's true. Except for those are the largest ones, so they're the most offset. I mean, those are larger than my cells.
Those have a separate problem.
Yeah, it's not one-to-one comparison, but yeah.
Okay, it's lunchtime. Let's thank all the speakers again.
And we see that these models become more and more complicated. However, for star formation prescription, for star formation we use the same prescription which we used 20 years ago. Basically, we parameterize star formation rate as and I changed the title of my talk a little bit. Yeah, I'm going to talk about implementation of non-universal star formation prescription in galaxy formation simulations. I'm doing this work at the University of Chicago with Andrei Kravtsov and Nick Nedin. Efficiency at which a gas is converted into stars at freefall time. And for this parameter, star formation efficiency, we assume that it's universal at level of few %. And we confine by hand star formation. Star formation prescription is as important part of stellar feedback loop as a recipe for feedback itself. And the feedback models are being refined for years. We had a special session on them, only to regions of cold and dense gas. So these temperature and density thresholds are usually set by hand. Sometimes other thresholds applied, like gravitational boundiness or convergence of velocities, but